Hello, everyone. My name is AKM Amanatullah, and I'm doing my PhD in UBCO, supervised by Dr. Khalad Hassan. Today, I'll be presenting the paper Holobar, titled Rapid Command Execution for Head-Worn AR Exploiting Around the Field of View Interaction. And this paper was published in CHI 2021. So this is the table of contents. So first, we will look at the motivation behind developing Holobar, and then we will get an overview of the system. Next comes the related works that have been previously done and which have motivated or helped make this research. Then there are two studies performed in this paper, so we will discuss them, and I'll summarize the findings. Finally, we look at the limitations and scope for future work. And to elucidate the limitations and my suggestions, I prepared a small demo that hopes to overcome the drawbacks of this study. So from the picture, we see a typical action done on the HMD. And this usually requires the user to activate a menu. And once it's activated, it's then displayed on the field of view of the head-mounted display. To interact with the menu, the user has to use his hand to select or validate an action using a mid-air gesture. But this has some problems. So the current system has some problems, which is displaying the menus in the field of view occludes the displayed contents, and also it limits the menu size. And on top of that, the mid-air gestures are rather difficult to perform accurately. So as discussed, the head-mounted displays have a limited input capacity. Also, displaying the menus in the narrow field of view occludes the content and also the menu, and these gestures are hard to perform. So these three are the major problem of the current head-mounted display. Now, the solution to the problem is one solution is combining a smartphone with the HMD to improve this process. So this has a few advantages. First one being it extends the field of view of the head-mounted display. So the user has more space to interact. And next, it uses the accuracy, the tactile motion, the tactile input system of a smartphone, and that helps speed up the process. Finally, it augments the number of input degrees of freedom. So this means the user has more space or more options to interact with the system. So now we will see an animated video provided by the authors to the conference to get a better idea of the system.
To activate the Holobar, the user brings the smartphone under the field of view and enters what we call the activation zone. The top level menu is then displayed on the field of view of the HMD and the second level menu on the smartphone. This layout limits view occlusion on the HMD and allows for a preview of the second level items. To select the top level menu item, the user can move the smartphone horizontally under the field of view.
So as demonstrated in the video, the authors present a novel approach to interact with multi-level display. Now, it has some principles, and the first one is it allows rapid activation. So anytime the user wants to use the Holobar, he brings his smartphone to the activation zone to activate it. And then the Holobar limits occlusion as it has all the second level menu items on the phone. So, and it also provides the preview. As it has the second level items on the phone, he can see what the second level items is when he goes to the first level item. Finally, it allows implicit selection. So what happens is the user has to move the phone under the first level item to get a preview of the second level item. So he is not knowingly or implicitly selecting the top level item when he moves the phone. So these are the 4 principles of Holobar. Now we will look at the related works. So the authors have first looked at the menu properties in AR, VR, or mixed reality settings. And the first paper focuses on various types of menu systems that are used in VR environments. And they suggested that hand gestures often suffer from ambiguity without appropriate feedback. So they require some form of graphical assistance. So that's and for the second paper, it proposed a menu system that appears at various parts of the body. And what they found was that existing studies normally use the hand as a reference for the VR objects, but these systems did not provide a tactile feedback. So using the tap menu, they could provide the tactile feedback by scrolling or dragging across the body parts. For the third paper, it is one of the earliest works done on manipulating objects using the head as a controller. So next, the authors then look at the interaction techniques in such settings. So the first paper here shows the interaction techniques using the head. However, this has some problems, which are that it causes neck fatigue and also motion sickness. Also, it causes a lot of unintended selections. The next technique uses the hand for interaction. So it uses the paper here uses different hand poses as a way of interacting with the AR objects. Now, there are other approaches that include leveraging the body parts and body motion for menu selection. And one of the examples is this third paper, which uses the palm as an interaction menu. So the palm of the hand is used to show the menu. So the authors finally looked at the papers which combined the mobile devices and also the head-mounted display. So one of the earliest papers to do that was the first one, and it used a handheld computer to alongside a whiteboard to make text entry or slight modifications easier. So for the next paper, it used the HMD to enlarge the display size of the phone. So it extended the display of the smartphone using the HMD. And there has been works that use the smartphone to extend the HMD. So it goes both ways. So the HMD can extend the phone, or the phone can extend the HMD. So works like this have been done. And the final paper, which is very important for this research, is the track cap. And basically, the researchers in this paper use the technology of the track cap to determine the location of the smartphone with respect to the head-mounted display that the user is wearing. So these were the related works. So we have looked at the related works, and also we have the overview of the system. Now, the authors have performed two studies to evaluate the holobar. And the first one looks at the smallest activation distance for the holobar. And the second one investigates the performance of the holobar for executing commands for a two-level menu. So this is what the authors wanted to see from study one. As you can see in the picture, there is the field of view of the HMD, and just underneath it, there are options to select the activation zone. Now, the authors wanted to see what is the lowest angular distance that they can set that will work perfectly for the holobar. So it could be 10 degrees, 20 degrees, and 30 degrees. The lower the angular distance, the easier it is for the user to activate the display. However, if they kept the angular distance too small, then there were some errors. in selecting the activation. So basically, if the users had a small activation distance, then it's easier to separate the HMD from the smartphone. So the first goal of study one was to identify the smallest distance for the holobar to be activated. On the other hand, a small activation distance will require the user to lift the phone further up, and it will risk increasing the activation time. So, the authors also evaluate the impact of different values of the activation distance in terms of completion time and ease of access. Now, for study one, the participants had to do 3 tasks, and the first task was to activate the holobar, so bringing it close to the activation zone. The second task was to select a highlighted item in the top level menu. Notice that for this task, they only have one level, which is the top level menu. And finally, they have to validate the task through a button displayed on the smartphone. So these were the 3 tasks, and the system that was used for this task was the Microsoft HoloLens, and then the smartphone that was used was the Galaxy S7 with the displayed body measurements and screen size. And finally, they had to track the phone with respect to the HMD, and that was done by OptiTrack system with 12 cameras, which was similar to the track cap that was in the related study. So the first independent variable that was important for study one was the head inclination. So there were 2 variants, where in the first variant, the users had to look at straight, and for the second variant, the users had to do the task while their head was tilted 20 degrees. Now, the next independent variable for this study is the activation distance. And these had 3 values. So this is the major independent variable that the authors wanted to see the difference in the answers. So the 10-degree angular distance, the 20-degree angular distance, and the 30-degree angular distance. So for the entire procedure, there were 3 independent variables. One, which we discussed, is activation distance. The second is inclination. And the third one is whether the users used the dominant hand or not. And next, they used a within subject design. And then the order of the factors was counterbalanced using the Latin square. So in HCI, what happens is if one user performs one method first, they could have a learning effect. So they could learn the other task better. So what they do is they shuffle the order of the task so that there is no impact of the learning effect. So there are two designs. One is within subject, and the other one is between subject. And basically, the order is shuffled in the within subject one to make so that the users don't, like, the learning effect doesn't impact the experiment results. And then, so based on the conditions, there were 180 trials per participant, and each participant took 25 to 35 minutes to perform study one. So the dependent variables were the activation time of the holobar, the completion time of the entire trial, and also the evaluation of the fatigue from the users. Now, the participants were all master's and PhD students, and 2 of them were females. And these are the other information about the participants. And one major thing is only 2 of the participants had previous experience with augmented reality applications. Now for the results of study one. So basically, the 30-degree and the 20-degree had a lower activation time. So for the 20-degree, it was 367 milliseconds, and for the 30-degree, it was 340 milliseconds. And also, it had the overall lower completion time. So 30 and 20 performed relatively well. And there was no fatigue in any of the three cases. So basically, as discussed earlier, it's beneficial to have a lower angular distance for this case. So the authors went with the 20-degree based on study one. Now for the second study. So the second study compares the Holobar with the default HoloLens menu. And to keep the things similar, the authors made another menu, which is the hybrid between the Holobar and the HoloLens. So this was how the hybrid menu looked like. So this is, for the Holobar, it's a linear menu, and for the HoloLens, it's a grid menu, but for the hybrid menu, it's a mix between linear and the grid. So for the goal of study two, the authors mainly wanted to see the performance between the Holobar and the two other menus. The one important other goal was they wanted to evaluate what is the maximum number of menu items that they can keep, that they can accurately point to. So the tasks for study two were basically same as task one, the study one, but what it had extra was the selection of the second level item. So this was the extra part for study two, and the apparatus for the study two were the same as study one. Another thing that is included is the there is a new independent variable. So they understood that in a normal scenario, the user would have the menus memorized, and to test to have the same effect or to have the same scenario, like having the menu memorized, having the menu memorized, they kept another independent variable where the users were given graphical instructions and one where they were not given any graphical instructions. And the other independent variable is the top level items. So they had a variations of 6 items, 8 items, and 10 items. And this made the independent variables tree, where first was the basically the technique type or the menu type, and the top level items and the graphical instruction. So now they followed the similar design as study one, and but this experiment lasted 60 to 75 minutes. And for the dependent variables of study two, they are the activation time, the completion time, and the evaluation of the fatigue of the techniques. The participants were the MSc and PhD students, and they had slight variation of the participants, but they were more or less the same as study one. From study two, it's clearly visible from the graph that the Holobar outperforms the other two menus. And this is for the total selection time, the top level selection time, and also the second level selection time. So the Holobar also performs faster than all the techniques, irrespective of the number of items or whether or not graphical instruction is provided. And from the third graph, we see that the one important observation was if the menu item was closer to the dominant hand, the participants took less time in all of the techniques when selecting that item, if it's on the dominant hand side. Yeah. So another thing that is showcased in the study is that the Holobar has the highest accuracy out of the three menus, and the post-study rating by the users revealed that the HoloLens actually was the easiest to use, followed by the Holobar, and the hybrid one had the highest fatigue. So while the results from study two showed that there was a clear advantage for the Holobar, the authors then realized that it is unfair to compare air tap as a baseline compared to a touch input for the Holobar. So they further investigated the validation technique by considering another input type. So that was the clicking in HoloLens. So they used the clicker in HoloLens and then compared how it stood up against the Holobar. And for the results, they found that the Holobar was still faster and outperforming the clicker HoloLens. But in this case, what they realized that if you see the Holobar and the HoloLens for the top level item selection, it's basically the same, but overall, the Holobar is still faster. So to summarize the research, the Holobar is a novel approach for command execution, and it offered a multi-level menu selection, which can be activated without occluding the user content. And the most suitable distance for activation was found to be 20 degrees. And finally, it was faster than the HoloLens by at least 29%, with a success rate of 99.4%. Now, for the limitations, the authors did not address the problem of switching applications in Holobar. So they just did one application, and they could have implemented they could do multiple applications, and then they could have a system to switch between them. So that could have been one improvement. Another thing was the selection was all in one dimension, whereas in the real world, for VR, AR, in cases like this, usually it requires a multiple, it requires manipulation in multiple axes. So that could be worked on. And another thing is the tracking of the smartphone with respect to the HMD was very costly. They required 12 cameras and an OptiTrack system to do that. So these were the limitations. So for the future work of the paper, they could work on their limitations. So using the depth and the tilt action of the smartphone, they could switch the application or do an action which in multiple axes. And also the top level menu can incorporate multiple dimensions. So they could have went inside the z-axis using some kind of gesture, and that could be worked upon because that's a limitation. And one other thing I could suggest is using the front camera to track the HMD and then select item. So that won't require the OptiTrack system that they used. So looking at the limitations, I am planning to work on the limitations. So using the front camera could be a better alternative to getting the position of the HMD. And also the depth information can be easily added if a user is using a smartphone. So taking these things into consideration, I started working on the limitation and developed our system in Unity so that I can use the depth information to change the item, and I can go from front to back using the distance from the phone to the user, and also the orientation of the face to change the position. So that can easily be used without the OptiTrack system, and here's the demo. So playing the demo.
So first of all, I'm looking forward. So the middle car is selected. If I want to select the green, then the purple, then this police car. And if I want to select the cars that are in the back, I just have to move it further away from my face. So
yeah, so this was my presentation. Thank you for your time. And these are the references that I referred to in the slide. Have a nice day.